Okay, let's continue with notes from chapter 3.4. We've talked about the concavity test, which allows us to determine whether where the graph is concave up, where the graph is concave down, and also where point of inflection occurs. The second derivative test, this name is a little bit misleading because this does not tell us anything. We use a second derivative, but this does not tell us anything about concavity or point of inflection. What the second derivative test, this term, is referring to is a test to determine relative extrema, the max and relative mins, the hills and valleys of the graph, and not for the point of inflection or concavity. So basically, this second derivative test achieves the same result as the first derivative test. With the first derivative test, we're simply finding critical points, testing the regions to see whether the graph changes from increasing to decreasing or from decreasing to increasing to determine max and min. Here, we're going to use the second derivative function to determine the same thing, relative max or relative min. Okay, so the way we do that is we plug a critical number from f prime into f double prime. So we first need to determine the critical number from f prime. These are the potential candidates for max and mins. We take these critical numbers, we plug them into the second derivative, and then we check to see whether we get a positive or negative value. If we get a positive value, that means we're going to, at that point, the graph will have a relative minimum. If we plug a critical number that comes from f prime into the second derivative, and if we get a negative value, then that x value will produce a relative. We know that the graph, the point on that graph will be a relative maximum. Now, it may seem kind of strange that a negative value will produce a relative minimum. Sorry, a positive value will produce a relative minimum, and then concave down, or where f prime is negative, will produce a relative maximum. That seems kind of strange, so I wanted to kind of give you a visual as to why that's the case. And then before we do that, though, if we plug a critical number that comes from f prime into f double prime, and if f double prime gives a 0, neither positive nor negative, then this test is simply inconclusive, meaning that this could be a relative max, it could be a relative min, it could be neither. We will need to do further investigation, probably having to use the first derivative test to determine whether it's a relative max or relative min. Okay. Okay, critical numbers from f prime indicates candidates for relative max and relative min. So let's say we found the critical number from f prime, and that critical number was x equals 1. And we know f prime of 1 will give us 0 because that's a critical point that's causing the slope to be 0. Let's say that point is part of a relative minimum graph. Okay. And we want to use a second derivative. Now, if we plug this x value into the second derivative, we're going to get a positive value because this point, if it is a relative minimum, it will be part of a concave up graph, right? So if it's part of a concave up graph, then the second derivative at that point will produce a positive value. Okay, so that is why if f double prime is positive, if f double prime of the critical number from f prime gives a positive value, then we know that the graph will have a relative minimum at that critical point. Okay. Likewise, if let's say the critical point that we're testing is at 0, let's say 0 is a critical point from f prime, will give us a slope of 0, and we plug that critical point into the second derivative and we get a negative value. Well, if it is a relative maximum, then that relative maximum is going to be part of a graph that is concave down. And if it is part of a graph that's concave down, then it would make sense that the second derivative at that point will be negative. So we know there's a graph will have a relative max at x equals 0 because of these two conditions. The graph has a slope of 0, and it is part of a graph that is concave down. So again, when you see second derivative test, this is testing for relative extrema, not point of inflection. So here are the steps we're going to follow. we're going to find f prime first, find the candidates for relative max and relative min. So we set f prime equal to 0 to find our critical points. Again, it can come from numerator or denominator. Now, once we find those critical points, we plug them into the second derivative, of course, after we find them. So we plug them into the second derivative. Now, if that critical point from f prime is producing a positive value from f double prime, that means it's part of a concave up graph, therefore relative minimum. If that critical point from f prime is plugged into the second derivative and we get a negative value, then we know that that point where the slope is 0 is also part of a graph that's concave down, and therefore that point must be a relative maximum. Okay, and if f double prime is 0, then test is inconclusive. We have to go through another method to find relative extrema. So example 2, find the relative extrema for a function using the second derivative test. So f prime, we first need to find f prime. We need to find the candidates for f prime. Go through power rule. We get 3x squared minus 8x minus 3. Set the derivative equal to 0 to find our critical points. We get negative 1/3 and positive 3. So now these are our potential candidates for relative max and relative min. These could be hills and valleys of the graph, but rather than using the first derivative test with a sign line, we're going to plug this into the second derivative to test, to use those rules. So before we can plug this in, we need to identify the second derivative. So we go through power rule once again, go through derivative rules there. 3x squared becomes 6x, negative 8x becomes negative 8, negative 3 is a constant, will go to 0. So now we're going to plug each of these candidates into the second derivative function. So negative 1/3 gets plugged into x. We get negative 2 minus 8, which is negative 10, which is less than 0. So if a graph has a slope of 0 and is part of a graph that is concave down, then we know that the graph must be sitting at a relative maximum. So the relative maximum will occur at negative 1/3 because f prime of negative 1/3 is 0, slope is 0, and is part of a graph that is concave down. All right. Let's test the other point. So if I plug 3 into the second derivative function, I'll get 18 minus 8, which is 10. 10 is greater than 0, so we know there's a relative minimum there because it's part of it's coming from a point where we know the slope is 0, and it's also part of the graph that is concave up. So if it is a point on the graph where the slope is 0 and part of a concave up graph, we know that this point must be sitting at a relative minimum.